Hello and welcome back to Geometry 101 Continued. We are looking at similarities, but instead of starting the discussion with the agenda, etc., let's start with a very straightforward problem and then figure out the theory and then return back to problem solving. So, this is a problem given to me. There is a triangle ABC. In this triangle, this line DE is parallel to BC. So, this line is parallel to this line. Furthermore, the ratio of AD is to DB, AD is to DB is given as 3 is to 2. And your question is, what is the ratio of the area of the triangle ADE to the area of the triangle ABC? So maybe hit pause right now and try and solve the question by yourself. A fairly straightforward question, grade 0 level application of similarities. So I'm assuming for this session that you are familiar with similarities. If not the in-depth proof and everything, just the key results at least, so that you know what is going to happen in the story. So I hope you tried that. Let's get cracking with the story. Line DE is parallel to line BC. That means this angle is going to be equal to this angle. Why? Parallel lines, transversal, corresponding angles are equal to each other. Same logic, this angle is going to be equal to this angle. So angle C is equal to angle E. And angle A is common to both the triangles, the big triangle as well as the small triangle. That means if I look at the small triangle and the big triangle, I see the three angles of the small triangle are equal to the three angles of the big triangle. That kicks off an idea known as triple A similarities. In fact, triple A is also not needed. Just having two angles of two given triangles being equal to each other was enough to kick in similarities. So what I can say now is that triangle ADE is similar to triangle ABC. Now in similarities we have to pay attention to correspondence. What corresponds with what? A corresponds to A, no problem. D is equal to B, so D corresponds to B. E is equal to C, so E corresponds to C. Because if I have written it in the right correspondence form, the ratio making, which is the next key result or the whole advantage of similarity, is having these ratios AD upon AB is equal to DE upon BC is equal to AE is equal to AE upon AC. So this is key idea number one for similarities, that if I say two triangles are similar to each other, the ratio of corresponding sides is going to be same for all the three sides and all the verbal interpretations around it. For example, taking the side of this triangle, multiplying it by a particular number to get to the bigger side and multiplying all the sides with the same number. So the idea of a constant relationship between all the sides. But this is enough for me for problem solving. I want the ratio AD upon AB. I have the ratio AD is to DB, AD is to DB, 3 is to 2. So let me call this 3x and this is 2x. So the ratio of AD is 3x and the ratio of AB is going to be 5x. So xx gets cancelled. The ratio is 3 by 5. Now this ratio is kind of constant, so for the other sides the ratio is going to be the same. So in a simpler problem, if I told you that this is 4 units and I asked you what is this, you could have said the ratio of DE to BC is going to be the same as this, so this would be 4 upon x, and then you can figure out the value of x. Essentially, before getting there, we're also quickly revising the key idea involved. So this is the idea of having the sides ratio equal to each other, and a very simple application. But our question was about the area. Now if we have already done similarities, the idea is very easy. The ratio of area, if I'm thinking of these two triangles, the ratio of area is going to be the square of this ratio. So if the ratio of sides is 3 by 5, the ratio of areas is going to be 9 by 25. And if you're wondering why have I squared, it's a very good idea to ask questions why, but luckily for me, I have already answered this question in an earlier video. on similarity. So maybe find that video and go through that, because otherwise with each proof it gets longer and longer. So think of this more of a problem solving session and key results being repeated. The ratio of sides is obviously equal, and the ratio of the area is going to be the square of the sides. Any of these will do, because anyway they are all equal to each other. So quick repetition of the basic idea: if two triangles are similar, the ratio of their sides is fixed, the ratio of corresponding sides is equal to each other, and the ratio of area is going to be the square of the ratio of sides. So pretty much the same question, same data. The only difference is now I am saying find me the ratio of the area of triangle ADE to the area of the trapezium DEBC. DEBC, or whatever you have named it. So the ratio of this area, the small triangle, and this trapezium. So you want to find this ratio. Actually, this should not be too much of a challenge at all, because you just figured out that the ratio of triangle ADE and triangle ABC you figured out was 9/25. That means this triangle is 9 and the whole triangle is 25. The whole big triangle is 25. Out of the big triangle, if you take out this 9, you are left with the trapezium DEBC. So 25 minus 9 is going to give you 16, and you have your answer already. The area of triangle AD would still be 9, but for the trapezium this would become 16, and you have your answer. So once you have the tool right, you will see such a problem will become very easy. And in fact, if you know the idea, the problem solving will be very fast. You have the ratio of these two parts. You want the ratio of this to the whole thing, you get the ratio as 3/5. You square it, because the area ratio has to be squared. So this will become 9/25. And from 25, you subtract 9, you get 16. This becomes slightly bigger because I am trying to explain and cover all bases, etc. But final problem solving can be very quick. So same story, there is a triangle ABC. I draw a line DE parallel to BC, which very quickly makes these two angles equal to each other, these two angles equal to each other, and this is the common angle. So the small triangle is similar to the big triangle, that is fine. That means the ratio of corresponding sides is going to be equal, that is also fine. That means AD upon AB is equal to AE upon AC is equal to DE upon BC, right? And this time in fact it is going to be faster, because this ratio is given to me in very direct form. So this ratio is going to be 4/5. So using this ratio, once again, obviously the question could be about the sides, and that would be very easy. The question is about the ratio of areas once again, and the ratio of area is going to be a direct square of this. So this would be 16/25. So maybe I should have started with this problem, because this is easier than the one before. In the other one, you just had to figure out that the ratio given in the previous problem, say the ratio given was 3:2, and of AD to DB, you had to figure out that this ratio is not the ratio of corresponding sides. You have to manipulate this a little to get the ratio of corresponding sides, and namely convert this into 3:5, or 3 to the total, which would be 5, and then you are good to go. In this case, that problem was already solved. Just a quick repetition of key ideas. So just extending the story a little bit, just to play around with the idea a little bit. In this story, once again, it is given to me that DE is parallel to BC, PQ is parallel to DE, PQ is parallel to DE. That means these three lines are parallel to each other. So obviously there is a hint here. Whenever you see parallel lines inside a triangle or any other figure where triangles are being formed, it is a very good clue that you can throw in similarity and it might work for you. So these three lines are parallel to each other. What that tells me is that triangle APQ, this triangle, is similar to triangle ADE, triangle ADE. Why is that? Because this angle is going to be equal to this angle, this angle is going to be equal to this angle. So if I think of the small triangle and the big triangle, I have two angles being equal to each other. This is one pair and this is another pair. Having two angles equal to each other is enough to say these are similar to each other. That means the ratio of sides will kick in. AP upon AD is equal to PQ upon DE, and is equal to AQ upon AE. The only challenge occasionally is going to be the correspondence, but in such a figure even that is not there, because I know what side matches with what side. So I know this ratio is going to be fixed, and I have a ratio. I have PQ upon DE. I have PQ upon DE. That means all of this is going to be equal to 4 by 5. And say now my question is, what is the ratio of the area of the triangle APQ? So triangle APQ to the ratio of the trapezium, let's say DPQE. Sorry, not the triangle, the area of this and area of this. So I know the ratio of corresponding sides is 4:5. That ratio is fixed for all sides. The ratio of the area is going to be square of this. So if I do a square of this, I will get a 16 and a 25. And remember this relationship, you're looking at triangle APQ and triangle ADE, this small triangle and the big triangle. That means the small triangle is 16 and the big triangle is 25. So this part, the leftover part, is going to be 25 minus 16, which will give you 9. So if this triangle is 16, this triangle is 9. Again, we don't have the specific area. The ratio of the areas is going to be 16:9. How did I come to that? I have the ratio of the big triangles, the small triangle and the big triangle. And from the big triangle, if I remove the small triangle, I'm left with this. Just playing with the idea, and let's go take the story further. And now I ask you, what is the ratio of this trapezium to this trapezium? Or maybe this problem wasn't given at all, and straight away you were asked, what is the ratio of this to this? That would be a slightly bigger problem than what we have dealt with. And do I have a ratio playing out for me? Yes, I have a AD is to DB. That means if this is 5x, this is 1x. That means if this is 5x, all of it is 6x. That means if I want AD is to AB, I will say the ratio is going to be 5:6. Add them up. So I have the ratio of AD is to AB. Why is that needed? Because once again I am thinking of similarities. And this time I am thinking of the similarity. AD is to AB. That means the triangle ADE to the triangle ABC. So triangle ADE similar to triangle ABC. That means AD upon AB is equal to DE upon BC is equal to AE upon AC. So far we haven't used this a single time, but just repeating the idea over and over again. So AD upon AB I have as 5/6. So this is going to be 5/6. And if I think of the area, it is going to be 25/36. That means this triangle, if this triangle is 25, this whole triangle is going to be 36. And if this triangle is 25 and the big triangle is 36, this part is going to be 11. And if this triangle is 25, you have already figured out that this is 16 and this is 9. So if you wanted the ratio of these two, you have 9:11. If somebody said, give me the ratio of these two, the ratio is going to be 16:11. So a slight bit of complication, just stretching the story, practicing the story. But even now, life is very, very easy, because it was given that these lines are parallel to one of the sides. Plus I have kept the orientation straight. So it is a very straightforward application, just so that we are comfortable and familiar with the idea. And now we want to change the orientation and make the finding the corresponding paths just a little bit more challenging. So in that direction of finding the corresponding path slightly more challenging and seeing the similarity play out in not the same story over and over again, let's try out this example. This is the figure given to me. It is given to me that angle ADE is equal to angle ABC. So this angle is equal to this angle. Angle ADE is equal to angle ABC. Writing this down is not very important. The whole aim is to be able to do it just by touching it and in your head without really having to capture all of this information, because it is captured already. This angle is equal to this angle. And these paths are given. AC is 9, CD is 11, AE is 12, and EB is inquired about. So let me try and think of how to apply the similarity here. And let me find the similar triangles first. So this is one triangle. This triangle is ACB. The first triangle can be written in any form. I saw A, then C, then B. I wrote it in that order, no problems. And the other triangle is this triangle, triangle ADE. But before writing this triangle down, let me think of correspondence and if they are similar at all. If I think of these two triangles, right now I have not written it in order. The triangle, I am talking about triangle ADE. So not in order yet, we will match the order in a bit, but just to refer to this triangle. If I think of this triangle and this triangle, I have angles equal to each other. This angle is equal to this angle. This angle is common to both the triangles. In this triangle you have an angle A, in this triangle you have an angle A. That means between these two triangles, once again, you have two angles equal to each other, and therefore you can definitely say that these two triangles are similar to each other. And now let's talk about the correctness in correspondence, right? So say I want, and I start with AC, and AC corresponds to what? So you know these two angles are equal to each other. So you know these two angles are equal to each other, and this AC is opposite to angle B. Angle B is equal to angle D or corresponds to angle D. That means opposite of angle D, what will you find? You will find AE. That means AC corresponds to AE. So instead of A, I will obviously have a A because A is the common point, but instead of C, I can write an E. So even in this story, I've gone for writing down the side first rather than the terms or the vertices. You can reverse the order and everything will pretty much the same. The challenge is it will remain the same. So AC upon AE, I have one ratio. Do I have AC upon AE? AC is 9, AE is 12. Now I have the actual ratio. Most of my work is done. Using the same similarity, I am thinking of triangle ACB, and this triangle ADE. I have already written down AE, I just have to throw in D. So now writing the correspondence can be more mechanical and obvious. AC upon AE is the same as CB upon ED is the same as AB upon AD. So just a couple of careful steps and you're back to your normal story after that. Okay, so now what did I want to find? I wanted to find this part. Let me call it X. BE is X. Do I have a BE in this story? I don't have a BE in the story. But I do have a AB, which is made up of AE and BE, which is 12 plus X. So instead of AB, I will write a 12 plus X. Do I have AD in that case? Do I have AD? Yes, I have AD because I have AC and CD. If I add them up, I have AD as 20. So you have a relationship 9 by 12 is equal to 12 plus X upon 20. I'm sure now you can figure out the value of X fairly quickly. So the only challenge in such a question is finding the correspondence. So I thought of one side, matched it, and after that it was fairly easy. If you want to think in terms of angles, you can do that. And let me just name the triangle differently this time. Let me call this triangle BCA. So I'm thinking of triangle BCA. What point corresponds to B? D corresponds to B because these two angles are equal to each other. So when I write a similarity, B corresponds to D. A is common to both of them. In this story, A is written in the last spot, so write A in the last spot. So if you are thinking of this triangle, which is made up of ADE, A is gone, DE is gone, you're just left with writing E. So it's not too much work after a first couple of steps or maybe the shock of applying it. But remember, this is like jumping from 7th grade to maybe 9th grade. In 8th grade, a lot of times they skip a topic. but returning to a topic after one level up essentially. So now you have a firm grasp of the similarity concepts. Now you have to find it in different kinds of figures and then apply the story. So this is our next story. ABCD is a parallelogram. That means AB is parallel to CD and AD is parallel to BC. That also means that this side is equal to this side and this side is equal to this side. Furthermore, AE is to EB is given as 2 is to 3. I have already put in that as 2x and 3x. CF is to FD is given as 3 is to 7. So I have converted that into usable 3y and 7y. And the question is about the ratio of areas once again of the areas of the triangle DFG. So this triangle and this triangle. So let me first think if they are similar, because then I have some ratios playing out for me. Let's see what can be done using that. So because these two lines are parallel, this angle is going to be equal to this angle. Why? These two lines are parallel, this is a transversal, these are alternate interior angles. Using the same logic, let me mark it so. This angle is equal to this angle. Same logic, two parallel lines, transversal happening. So this angle is equal to this angle. These are vertically opposite angles anyway. So these two angles are equal to each other. That means all three angles are equal to each other. That means this triangle is similar to this triangle. That means my only challenge is now finding the corresponding term. So that's it. So let me start with this triangle BEG. And because I have written it BEG, let me find the corresponding point. So angle B is equal to angle D. So instead of B, I will write a D. Angle E is equal to angle F. So instead of E, I will write an F. And G is common to both. Now once I have this, I can get the ratios going. So if I look at the ratio of corresponding sides, EB corresponds to DF or BE corresponds to DF. So this is great, and you might want to put 3x and 7y, right? But you don't have x and y's value, so just keeping it in this form is not going to work for you. What other property can you use? The other idea that you can use is that AB is equal to DC, the opposite sides are equal to each other in a parallelogram. So let me think about that, and let me then think of EB in terms of AB. So if I say what is EB, EB is 3 by 5 of AB. This is 3x, this is 2x. So EB is 3x out of 5x or 3 by 5 of AB. So instead of 3x, let me write 3 by 5 of AB. Similarly, instead of DF as 7y, let me write DF as a part of DC. So that means this can be written as 7 by 10. 7, 3, 10, total is 10, 7 out of 10 of DC. And now you can cancel these two out. So 3 by 5 into 7 by 10. So this will give you this. And this can be worked out. 3 by 5 upon 7 by 10 will give you 3 into 10 divided by 5 into 7. So 5 2s are 10. You will get 6 upon 7. So go back to your original story, BE upon DF. Now you have the ratio as 6 is to 7, because 3x and 7y was not going to do it for you. Or if somebody made a mistake here and they said my ratio is going to be 3 is to 7, they have obviously made an early mistake in the process, and the understanding of ratios is most likely poor. So that is going to be an obvious error. But even if you said correctly 3x and 7y, but even if you made it to this point 3x and 7y, you still not get anything. Now I have a clear ratio of BE and DF, which is 6 by 7. So I have the ratio of corresponding sides, but the question was about the area. That means I will have to think of the square of these two sides. That means my ratio will become 36 is to 49. But there is a problem here, a basic problem that we started the process off with. BEG is to DFG is 36 by 49. You want it the other way around, so this is going to be 49 and this is going to be 36. So a very basic detail, don't get stuck here. This is the easy part. Most of the tough work you have already done. So another question of similarity, and once again the key is obvious. The parallel lines are there. which are making the angles equal, which is making the triangle similar. After that, and after finding the corresponding paths, there was a little bit of extra work needed, and that help was given by the parallelogram property that DC is equal to AB. So throw in a couple of ideas together and you're getting better at this. So this is our next problem. Again, looks slightly different, and this time in the story we have a trapezium. In a trapezium, two sides are parallel to each other. So AB is parallel to CD, or a pair of sides is parallel to each other. That is the definition of the trapezium. That is one part of the story. Furthermore, it is given to you that the area of the whole trapezium is 40 units. And you're also given AB and given DC. AB is 12 units and DC is 8 units. And now you are asked, what is the sum of the areas of the triangle DCG and the triangle AGB? So add these two triangles up, find the area and add them up. That is your challenge. So let's get started with the process. A couple of things I can figure out fairly quickly. These two lines are parallel. That means this is a transversal, this is a transversal. Alternate interior angles are equal to each other. Alternate interior angles are equal to each other. This is a vertically opposite angle. So two angles are equal. So this triangle is going to be similar to this triangle. Corresponding sides ratio, AB is in front of this third angle. DC is in front of this particular angle. So DC corresponds to AB, and it is quite obvious to me also. So let me write that down. AB upon DC is given as 12 upon 8. So I have the ratio of the bases or corresponding sides. And now I want to think of the area, and this time I just don't have to find the ratio, I have to find the actual areas because I want to add them up. So how will I go about doing that? That means I will have to think of the height of this triangle and the height of this triangle. So let me call this H1 and H2. The ratio of heights is going to be the same as these sides. That means this ratio is going to be H2 upon H1, because remember H2 corresponds to 12 and H1 corresponds to 8, so in that order. So that means I have the ratio of heights also, but this is not going to be enough for me, because once again the question this time around is not about the ratios, it is about finding the exact area, and let's say practicing one particular process. So I have the ratio of the heights. This could be a key result again, that the ratio of heights of two triangles in two similar triangles is the same as the ratio of corresponding sides. So one part of the story done. Now let me go for using this area as 40. What is the area of a trapezium? Area of a trapezium is half sum of sides 12 plus 8 into the height of the trapezium. Let me call it capital H. That means this whole thing is the height of the trapezium. Where is this formula coming from? And I hope you know where this formula is coming from, or are familiar or comfortable with this. If not, write it down somewhere. Area of a trapezium is half, very much like the area of triangle, base into height, but this time you will add up both the bases, this base and this base. Because if you want to go for a quick recap, say this is the trapezium, and if I draw a diagonal so, and I say, okay, what is the height of the trapezium? This is the height of the trapezium. This height is the height for this triangle as well as this triangle. That means if I find the area of this triangle and I add them up, I will have the area of the trapezium. Area of this triangle is going to be half base into this height. Area of this triangle is going to be plus half base 2 into the same height. So you add the bases and you get the formula for the area of trapezium. Not that that is a focus right now, but just in case. So using this, I can find the height of the trapezium. So this 2 goes there and this becomes 80, and I have 12 plus 8, 20. So H is equal to 4. So I know this whole thing is 4. Now what can I do? Remember, I have the ratio of H2 is to H1 is 12 is to 8, or that means H2 upon H1 is 3 by 2. That means H2 is 3 by 5 of the big thing, because this is 3, this is 2, this will be 3 by 5 of the whole thing. And what is the whole thing? The whole thing is 4. So you get 12 by 5, 2.4. So you know this is 2.4. 3x is 2.4. So x is going to be 0.8. 2x is going to be 1.6. So this is 1.6. Or 4 minus 2.4 gives you 1.6. And now I have the base as well as the height. I have the base as well as the height. Find the area of this triangle, find the area of this triangle, add them up, and you will have your answer, leaving that last step up to you. So once again, similarity gives you some part of the story, trapezium and the area of trapezium gives you another part of the story. Using the ratio, throw everything together and have fun with it.